and very much is nanoparticles used. So why using nanoparticles? And then what I am working on with my research is nanoparticle in treatment of cancer. And there is challenges in delivery of nanoparticles. So that is what I will cover. So, but just to remind you now, what kind of range are we talking about when we're talking about nanotechnology and nanoparticles? Typically, it's from 1 up to 100, perhaps some 100 nanometers. And if we compare that with other known systems, so if we start out there with a tennis ball, really large, and then just a period, typically a size of 1 million nanometers, a cancer cell, some 20 micrometer, bacteria, virus, 100 nanometers, and then here you have the range of where we work, say we have the nano size between a large protein like antibody and a virus. And then if you go further below, it will have smaller molecules, and down here in 1 angstrom, a water molecule. So how can we study then some things on a nano range? What kind of imaging technology do we have? Because now we're not talking about ultrasound, MRI, X-ray. That will be imaging modalities for the whole body. Now we have to use other kind of imaging techniques. And so here describes some of the kind of microscopy techniques that can be used. So if we, as you know, if you really have to have a very large spatial resolution down to molecule level and nano level, then we have to use electron microscopy. So if we work on optical imaging, light microscopy, then the smallest two objects that we can separate will be 200 nanometers apart. So we can hardly see any nanoparticles with light microscopy. So very much then will be on electron microscopy. And when we work on a nano range, then other kind of effects become important. Because of the small size, we have a large surface to volume ratio. As you know, the volume will go proportional to the diameter times to the 3, while the area is times to the second or square. So it's large volume, large surface to volume ratio. Several quantum phenomena will occur at this scale, and now also thermal forces comes into play. So the thermal forces might be more important than, for instance, gravitational forces, magnetic forces, and so on. So the thermal forces will then, that is just determined by the Boltzmann's constant and the absolute temperature. So that was just a little bit to say something more general on what happened on the nano scale. So what about nanoparticles and functional nanoparticles and diagnostics? So these figures contain a lot of information, so I'll spend some time trying to explain it. First, it says something about the size. As I said, from 1 to 100 nanometers, typical size of a nanoparticle. And then it says something about material. So a nanoparticle can be made of very many different kinds of materials. Here it is particles made out of organic materials and inorganic materials. And I will come back more to what kind of materials and how to make these nanoparticles. We talk about nanoparticles as they are something spherical, but it might have another shape. It might be like a rod or a cube or a star. So the shape can vary. And importantly, on the surface of such a particle, we can functionalize it. We can add some molecules so it can bind to certain cells or a certain properties, or we can coat it with something so to increase its circulation in the body. And inside the nanoparticle, there is where we normally will encapsulate a drug and a contrast agent. So when we are talking about contrast agents for imaging, it can be like imaging agents for MRI, some radioactive isotopes, and some dye. During the lunch today, I was sitting at the table and talking to Erik, and he made me aware of this very interesting review article here from Ghana. So I think you all should read this article. So I guess perhaps all of the authors are present at this summer school. Erik Manson, Francis, where are you? Yeah. Out. And Steven Income, as you met, and Ahmed Geda, and the title of this review, Integrating Image Fusion with Nanoparticles, Contrast Agents for Diagnosis, a review. So they have a very ambitious view that they can incorporate very many different contrast agents. So you can then use these agents for imaging with MRI, with CT, with the ultrasound, you may name it. So that is something to read. Coming a little back more to then the kind of material that is used and the kind of material that often is used for either diagnosis or for drug delivery. So very much it will be used, it will be inorganic material like silver, gold, iron, silicon, platinum, carbon that is used when we would use this particle for diagnosis. And very much then biosensing. The organic drug delivery with phospholipids, here is, you can see what is a phospholipid. Actually a liposome made of phospholipids. So these phospholipids, they have a polar head and fat acid tails. So this polar head, that likes water, while this tail, fat acid tail, don't like water. So when you place phospholipids in water, they will spontaneously form such a structure. They will spontaneously then form such a liposome. Very practical. And we had two people from here from Cape Coast University, Savannah and Jerry. They went to NTNU to learn how to make these liposomes, and then later how to use them. So this is the most common kind of nanoparticle used, but more and more other kind of materials has also been used. For instance, different kind of polymers. They can be synthetic or natural. And what we also can do, we can use a hydrogel and implant a hydrogel in the body. So it can contain then some, it will be made of some polymers and contain some drugs. So what we can have then is a more controlled release then of the drug into the body. So this was just a little overview of different kind of materials. And then just one slide on how to make these nanoparticles. Because the easy way to do it is just to mix it on the bench. Like I said, phospholipids, they will spontaneously form this kind of liposomes. But what if you mix polymer with a solvent just on the bench, you get nanoparticles with a range of sizes. And very often you would like them to be more, having more the same size, being more monodisperse. And then microfluidic channels is the method to use. So then you will have, for instance, here a solution with your phospholipids, and then a solution with the solvent. And then when it goes through this microfluidic channel, what you come out in the end is, in this case, if you use phospholipids, you will come up with liposomes with very much the same size. So a little more on diagnostics and these different kind of particles to use. As many of you know, iron oxide will be a good contrast agent for MRI. So we can incorporate iron oxide then in nanoparticle and use this particle to measure inside the body. Often you take out some blood from the patient and want to detect some molecules in the blood, and then the plasmonic behavior of nanoparticles from materials like silver and gold can be used. And just to explain a little more about this, what we call this localized surface plasmon, because when you have metals like silver and gold, they will have free electrons. There will be free electrons and oscillating on the surface of the particle, and those free electrons, that is what we call plasma. So if we now hit these particles with electromagnetic waves, for instance light at a certain frequency, they will then start oscillating, and you can see here how then the electrons will then move in the electromagnetic field. So it becomes like a dipole, and creating then this electronic field inside the particle. And then when you use light here, they will absorb light at a certain wavelength and then emit it. And then the size, the beauty here is that the size of this particle depends what kind of wavelength for absorption and emission. And also the shape of the particle, if it's nanorods, that if now is more and more elongated, then it will be more and more shifted to the red region of the spectral interval. So that is one application then of nanoparticles for diagnostics. Very many think of a nanoparticle as something new. Nanotechnology and nanoparticles is something new, but it is not. Liposomes started being used in cancer therapy in the 1960s, and some polymeric carriers even before. So we have had these nanoparticles for a very long time. What is coming more now the last years is been what is called nanorobots. So nanorobots, what is that? That is something, then you need something to convert then an external power source into kinetics energy of this nanoparticle or nanorobot. So nanoparticles, they will just be injected in the blood, they go through the blood, but with the nanorobots, they have an energy. So they will have an extra energy driving them, so they will go much, much faster. And there have been some papers suggesting that this kind of nanorobots can actually be used in microsurgery and go into the body, take out small biopsies, can be used for drug delivery, wound healing, and if you have a clot in the blood vessels, we use to remove this kind of clot. Okay, so that was a little bit about diagnostics. So now turning into nanoparticles in cancer therapy. So just remind you about the standard treatment of cancer. Surgery, you remove the tumor, everyone is happy, but very often you cannot remove everything, and you can combine it with ionizing radiation and with chemotherapy, and many of you here work with radiation, and now you know that that also will damage surrounding normal tissue. And so a challenge with the radiation, and especially with chemotherapy, is that normal cells is also sacrificed. And then if we think about how much of the drug, do you know how little of the drug injected into the patient actually accumulate in the tumor? Less than 0.01%. It's hardly anything of the drug that accumulate in the tumor. So that is a real problem. So how can the nanoparticle be used to improve this? So just first, like a summary of some advantages why using nanoparticle in drug delivery. I have already mentioned that we can have multifunctional nanoparticles, so you can encapsulate both the contrast agents for imaging and a drug. So then you can use the imaging abilities to monitor therapeutic response. Very many of the drugs are not water soluble, so then it's nice of them to have a carrier. We can have more targeted drug delivery. We can, on the surface of the nanoparticle, add a molecule that will bind to specific cells. And most importantly, we have an improved pharmacokinetics and increased circulation time in blood. So I will come back a little bit back to that, but that is really important, that when you have free drug, it will be leaving your body perhaps within minutes or an hour, while the nanoparticle can circulate for a long time, perhaps up to 24 hours. Then we will have an increased uptake in tumors of nanoparticles due to leaky blood vessels. Because when the tumor cells are growing, the tumor are not really able to make a good functional vascular system. So there will be some gaps, some space between the endothelial cells forming the vessel wall, and they are typical some 100 nanometers, which is perfect then for nanoparticles to cross. So I will come back more to this point because this is very important. And since then nanoparticles can cross this leaky vessel, but will not cross normal vessel because they are not leaky, we have less damage to normal tissue. So a little bit about the pharmacokinetics and the clearance. So the route of clearance, that depends very much on the size of the nanoparticle. So if you have very small nanoparticles, less than 5 nanometer, they will be secreted through the kidney. But most nanoparticles, they are around between 20 and 100 nanometers, so they will be taken up of some specific cells in the liver and then be removed from the liver. And if it's really large particles, then they will be cleared out by the lungs. And also the spleen has some particular cells that they also will clear out cells in the, or clear out particles in the range of 100 to 20 to up to some 100 nanometers. That was a little bit about how particles will be secreted. I mentioned the circulation time in blood, and this graph show you now the difference in how fast free drug, this drug doxorubicin, either injected free in the patient or in a nanoparticle. And you can see that when it's free, it will then be secreted within an hour, perhaps minutes, while the liposome, that goes on for a very, very long time. And that is important because you can imagine when you inject a drug in your body, you would like it to be able to go through the tumor many times. So each time it goes through, it can deliver. It can go into can leave the vasculature and go into the tumor and kill the cells. And if it is secreted such fast, would have a limited amount of drugs going into because it just secreted so fast. But with the liposomes, it would be circulating and circulating and have many opportunities to go into the tumor tissue. So then something about, I mentioned that one of the main motivation for using nanoparticles is these leaky capillaries in tumors, which is illustrated here. So here you have a vessel with the endothelial cells forming the vessel wall. This is a normal blood vessel. And here you have a vessel in the tumor. And you see here that between these cells that form the vessel wall, there are space. And if you look at this magnified image, you can see that this space is typically more than 100 nanometers. So perfect for nanoparticles to cross. And that is what has been illustrated here. Here, nanoparticles stay here in the vessel. Here, they cross the capillary wall and go into the tumor. Another characteristics of tumor is that they have very poor lymphatic system. In normal tissue, we will have a lymphatic system that reabsorb excess water and take it back to the blood. So that is illustrated here with this green. In normal tissue, we have lymphatic vessels, while in the tumor, we don't have that. So then the nanoparticles that is coming into the tumor will stay there. There are no reabsorption. So this is called then the enhanced permeability and retention effect, enhanced permeability of the vessel wall and retention because of the lack of lymphatic vessels. Okay, so I said that we have that liposomes since the 60s. So why are we not able to cure cancer? If it was so easy to incorporate a drug in a nanoparticle, why do we have a problem with cancer? Yeah, do you want to know? So the problem is to get the drug to all the cells. So this fluorescence image is taken from a mouse. We injected a liposome in the tail vein of the mice, and the liposome is here in blue. And this liposome contained a drug, doxorubicin, which was taken up in cells and is in green. So cells that has the drug, that is now in green, and the red is the blood vessel. So you see here that you have nanoparticles very close to the vessel wall, and the drug taken up in cells is also very close to the vessel. All this black area is cancer tissue. Cancer tissue with no drugs coming there. So, and if you think about it, which steps do we have to get a successful delivery? So, first of all, it needs a vasculature. We need blood vessels, which is like the highway. And then it has to cross the capillary wall, and explain to you that the blood vessels are leaky, so that might not be the most difficult step. But then the nanoparticle has to penetrate through this extracellular matrix, so what the material between the tumor cells we call extracellular matrix. And then if it's so lucky that it reaches a cell, it has to be taken up into the cell. I told you that of the injected free drug, it was less than 0.01%, and if that was taken up, and if we encapsulate it, it has been a paper that has gone through all literature, and they have now estimated that the median uptake of drugs encapsulated in nanoparticles is just 0.7. But it's more than a factor of 10 better. And another important thing when we talk about this transport is what kind of physical processes is responsible for this transport. And it's two physical processes. It's diffusion driven by the concentration gradient, and it's convection driven by the pressure gradient. So now I would go through some of these steps and talk about now the diffusion and the convection. So first of all, the vasculature. What is how does the vasculature in a tumor look like? It's very chaotic. So these two images to the left show typical vasculature in a tumor, and to the right in normal tissue. In normal tissue, straight, nice, cylindrical vessels. Here it's chaotic, and you have ends that end in nothing, and really high resistance for blood flow. Another problem for the nanoparticle being in the vasculature is that in the vasculature we will have cells that want to eat the nanoparticle. We have immune cells that want to eat the nanoparticles because they think they are something dangerous. So they will eat them. There will be protein binding to nanoparticle, and there will come cells eating them, and then we can coat the nanoparticle with something called polyethyl glycol. That will help then increasing the circulation time. So that was a little bit about what happened in blood. And then the next step is this to cross the capillary wall. And that I have explained to you that we are so lucky that we have these leaky vessels. And then I said that it was two processes. It was diffusion and convection. If we're going to have convection, we need a pressure gradient. So what is the pressure gradient across the capillary wall in a tumor and in normal tissue? Well, the blood pressure in the capillary will be the same in normal tissue and in tumor tissue, because that is determined by the heart. The heart is pumping, and we have then a certain pressure in the capillaries, typically 20 millimeter mercury. Then if you go out of the vessel in the normal surrounding tissue, it will be around 0 or perhaps even a little below. So here's really low pressure. But in the tumor tissue, we will have an interstitial fluid pressure, which is typically 10 to 30 millimeter mercury. So that is almost the same as the pressure in the blood vessel. So what then? You don't have a pressure gradient. You don't have convection. No pressure gradient here. Really a problem. And why? Why do we have such a high pressure here? And that is because of the leaky vessel. Because of the leaky vessel, nanoproteins and different stuff from the blood will cross the leaky vessel wall, and then water will follow, because the body wants to have the same osmotic pressure on both sides of a membrane such as the vessel wall. So then water follows, and we don't have any lymphatic vessels here, so we don't have a reabsorption of the water, so we get a high pressure. So that is a problem, this high interstitial fluid pressure. So then perhaps the most difficult step is to penetrate through the extracellular matrix. I said this extracellular matrix is the space between the cells, and that consists of a protein network. Here we see a protein network like collagen, and that is embedded in a gel of sugar. And that sugar is also called glycosaminoglycans. So you can imagine then you have a gel of sugar and protein network through which now the nanoparticle has to penetrate to reach each cells. And then if we look at the equation now for a flux through the extracellular matrix, we have, just look at the one-dimensional flux, we have a diffusion, then with the diffusion coefficient and the concentration gradient. We have the convection, where we have the pressure gradient and K is called the hydraulic conductivity, which is a parameter that says something on how easy water can flow through the tissue. And then we have the retardation factor, which says is if the velocity of the nanoparticle, the ratio between the velocity of the particle and the velocity of flow. But as I've now told you, convection, we hardly have any convection. So then we're left with diffusion. And what about diffusion? What about diffusion in a nanoparticle? That is really bad. That is really bad. Because the diffusion depends very much on the molecular weight of the particle. So here is now the diffusion coefficient as a function of molecular weight. And this is now small molecules up to 100,000 kilodalton. But then if you come up to a certain size, then it falls off very much more, much steeper. So, and on a particle, we are in this range. So we have extremely low diffusion coefficient. So, not good news. And then, if now the particle reaches cells, it has to go into the cells with the process called endocytosis. And then when it goes into the cells, the drug, which is inside the nanoparticle, has to escape the nanoparticle and then go into the nucleus, because most of the drugs, will bind to DNA and do some DNA damage. So, now you perhaps understand why nanoparticles and liposomes has not been that successful in cancer therapy. So what is the take-home message? Well, we started talking a little bit about the nanoparticles in the diagnosis, inorganic nanoparticles, and particularly the concept of plasmon resonance, organic nanoparticles where you can encapsulate contrast agents and also incorporate several imaging contrast agents, which is one of the aims for your people here in Ghana, and making then diagnostics. When it comes to treatable cancer, I've explained to you the enhanced permeability and retention effect, which will lead to an improved accumulation in tumor and less damage to normal tissue. But there are problems for a successful delivery to all cancer cells. So you can cross the capillary wall, but it doesn't reach all the cancer cells. There are problems eliminating from the blood, little nanoparticles across capillary wall, and especially poor penetration into the extracellular matrix and low cellular uptake. So how to obtain a successful delivery of nanoparticles to all cancer cells in the tumor? That will be a later talk. So thank you. Any questions? Well, you can. Well, I will be here for a week, so you can just come and ask, and we can discuss later.